Right, first, last time we studied more about the structure of the atoms, and then we talk about a very important concept called valence electrons. Okay, valence electrons are what? Electrons on the highest energy level, on the outermost shell of an atom. And those electrons are responsible for what? For chemical properties, okay, for their chemical properties, and basically for their reactions. And those electrons are the ones that are responsible for what? For binding, for chemical bonding, okay, either covalent bond or ionic bond. And in order to demonstrate the number of valence electrons and how they are involved in chemical bonding, okay, we use a very useful structure called the Lewis structure. Not only it will tell us how atoms are interacting with each other, but also can show the structures of what? Of molecules. Okay, this chapter we focused on the Lewis structure of molecules via covalent bond. So before we do that, let's go ahead on this board. Okay, let's board and erase it. Draw the Lewis structure of ozone again. Okay, draw the Lewis structure of ozone again. And to review the steps of drawing a correct Lewis structure. Okay, have you studied afterwards? What is the first step if I want to draw the structure of ozone? What is the first step of drawing a correct Lewis structure?
Find how many valence electrons.
How many total valence electrons, right? How many for ozone?
It's
18.
18.
How do we know it's 18?
6 for each oxygen.
6 for each oxygen, so 18. And why oxygen is 6?
Because it's in the 6th group.
6A group. Perfect. I like it. It's great. Okay, so 18 valence electrons. Then step 2 is what?
Make the thing to have 3 oxygens.
3 oxygen, and we can call it to give a skeletal of this structure, right? How the atoms are arranged to each other. We call it skeletal. And then what? These 3 oxygens, we have a central oxygen and what? 2 surrounding oxygens. And then what?
You put a bind between
A single bond between the oxygens, the surrounding outside oxygens with what was the central oxygens. And those 2 single bonds represent
2 each. So
2 electrons for each. So we actually used what?
4.
4 electrons. So that means we have 14 left. Okay, after we use these 2 single bonds. And then next step.
You would fill out the outside first. You would put 6 on each of the outsides so that they would each have 8. And then you would have
2 left.
2 left. And you put 2 in the middle.
2 in the central oxygen. Right? These are all the previous step, first few steps. Then we know we first satisfy the outside ones. So we know these 2 oxygens are what? Satisfied. Right? And only thing we need to look is the central oxygen. Is that satisfied?
No.
No? So what do we do?
You would make another bind with either the right or the left oxygen.
Either right or what? Or the left oxygen. So we end up with 2 Lewis structures of ozone. Okay, of ozone. Okay, of course we're gonna pick electrons 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4. And we call those 2 Lewis structures what? Resonance structures of ozone. So basically, the bond between these oxygens are what? Somewhere between what? Double and what? Single bond, because the double bond can what? Shift between these 2 atoms. Perfect. So that's ozone. We're gonna use this fact later. Okay, later after we review this. Okay, so then we talk about this Chapman cycle, showing us where the ozone came from, and also how ozone shields what? UV radiations, right? So this Chapman cycle basically shows in the stratosphere, even though the air is very thin, but we do have oxygen molecules which will be broken down into what? Into oxygen atoms. This is oxygen molecule, right? Oxygen gas into what? Into oxygen gases, no oxygen atoms. And of course, in order to break oxygen molecules, the UV here used is what? Is high energy UV. You can see the wavelength is lower than what? 240. And we know lower than 250 is what? UVC, right? UVC is between 200 and 280. So that means lower than 240 means very high energy UVC, the highest energy of all the UVs. And after that, the free oxygen atom, which are very active, right? Because they're what? They're not satisfied, right? They only have, oxygen has how many electrons? 6. So they're what? They're not happy. They want to grab what? Something. Okay, there's something. That's why they collide with another oxygen molecule fast to give what? To give ozone. This process is super fast. But once ozone is formed, ozone can serve to what? To absorb UV again. And this time, ozone absorbs what UV? UVB and what? UVC. Okay, UVB and UVC. Because anything less than 320 is what? UVB and UVC. So basically, UVB and UVC, both these UVs can what? Can break down ozone. Breakdown means what? The energy is what? Taken away, absorbed to do what? To break the molecule down. So the energy does not what? Reach us. And after breakdown, we know these two will what? Fastly collide again to give what? Reform ozone. That's why we have a subcycle showing what? The ozone will not be what? Depleted. Okay, if only for the purpose of absorbing UV. And finally, of course, if oxygen instead of collide into an oxygen gas, the oxygen atom collides to an ozone, then what? Ozone is what? It's quenched, it's removed. But we mentioned that the chance of this colliding is small, is low, and also the colliding is slow. So ozone normally will not be naturally removed a lot. And even it does, we have what? We have new oxygen filled into the cycle. So we always maintain a what? A good concentration of ozone. So that's how we explained where the ozone comes from and also how ozone shields UV radiations. Okay, and of course, the next page shows you free practice for you to help you to further understand this process. I'll leave A through C for you to work on yourself. I think it's very useful for work on the Chapman cycle. But 2 questions I want to explain with you. Okay, the first question is the D. Okay, I want to explain with you is, in contrast, the ground level ozone molecules react in a matter of minutes rather than months. Why is the difference? Okay, the context is, okay, the contact is C. What is C? C is to tell you, hey, how does ozone is removed? How is ozone removed from the atmosphere? We know ozone is what? Ozone is removed by what? By colliding with an oxygen atom. So ozone is what? Removed. Right? But we said this is what? Slow, right? Very slow. I mean, it takes maybe hours and months and years to remove ozone. Okay, that's why we're not concerning the ozone being what? Depleted, natural cause. But the question is, the ozone we're talking about ozone is what? In the stratosphere. But we do have ground level ozone, which are what? Bad gases. We learned in chapter 1. But those ozone molecules react very fast. What do you think the reason is?
Wait, so sorry, can you say the last part again? So
We said the ozone here, right?
Mm-hmm.
Ozone here react with O
Mm-hmm.
to get removed.
Mm-hmm.
And we say this process is slow. And in the question said is mentioned is actually the process takes a month.
Mm-hmm.
To what? To remove ozone, to react ozone. But these ozone are what ozone? The above us, the stratosphere ozone, the ozone layer, right? It takes months to what? To be removed. But we know in our ground level, like here around us, we do have what? Ozone in our air we breathe. But those ozones react fast, in minutes. Why do you think that's the reason? Yes. Not sure? That's fine. I mean, think about in the air. Okay, the reason ozone and O, they collide slow, one of the reasons is what? They don't have a lot of them, right?
Not getting broken down.
Correct.
So then,
You don't have a lot of ozone. Ozone, we know it's a layer, but the concentration is still what? Low. And also, in order for ozone to be removed, ozone have to collide with what? With the O. We know O always collide with what? O2, right? So the chance of these two collide is what? Is low. Why chance is low? Because there are many of what? These guys present. Is that right? But think about around us. The air is what? Thick, right? We not only have air, we have what? We have living things. We have dust. We have particulate matter. We have a lot of air molecules of what? Around us. So whenever there's an ozone can collide with what? A lot of species. To what? To react. Does it make sense?
yes, sir.
So the main reason is at the ground level, the molecules concentration are too high. So whenever there's an ozone doesn't mean ozone can only react with ozone can react with what? With many molecules in the what? In the atmosphere. That's why ozone will react in fast, in minutes. Okay, that's one reason. Okay, one reason. Another reason is you notice that in the CHEM cycle, we said in order to break oxygen, right? O2, we need what? UVC to what? To oxygen. Is that right? What is UVC? 200 and 280. And this is what? Even high UVC. But ozone, not only UVC can break it, UVB can also what? Break it. What is the reason? Why do you think there's a difference? Why oxygen you must need UVC to break it into what? Into two O's. But ozone, you don't need, I mean, UVC could, but UVB also could break down ozone to what? To O2 and O. What do you think the difference is? I gave you the structure already. Take a look at the structure. The answer is in the structure.
because
Not sure?
no.
Think about it. What's the difference between UVC and UVB?
Different energy.
And which one is higher?
UVC is higher.
UVC, this means what? This is higher.
Mhm.
So we can explain is we need higher energy, much higher energy to do what? To break this guy.
Mhm.
Not much energy to break this guy. Why do you think that's the reason?
Because it's like more spread.
More what?
Because there are 3 oxygens, so it's like
Not more oxygen. Take a look at the bond. The bond between O and O is what bond?
a double
A
bond.
double bond. The bond between these 3 O's is a what? A
It's-
double and single. And we talked about earlier here in this structure. The double and single means what? Means the bond between these O's is what? Kind of like a what? 1.5. Is that right? Hybrid, right? So think about double bond and 1.5 bond. Which do you think is stronger?
The double bond.
Double bond is stronger, right? More bond means what? Double bond means 4 electrons. 1.5, I mean, it's not 3 electrons, but kind of like weaker than what? Than the double bond. So that means you need a higher energy to break a stronger bond. You don't need that high to break what? A weaker bond. 1.5 bond. That's what the reason is. Okay. Of course, UVC, the high energy can break this too, but UVB with enough energy will also break what? Ozone too. That's why ozone not only absorbs UVC, but what? UVB. But oxygen will only absorb UVC. Okay, UVC. That's something we can explain based on what? The structure. We only have to know the structure in order to answer these questions. Okay? Next. Okay. We know ozone. Okay, ozone will be removed when ozone react with what? With oxygen to give two oxygen gases, right? O3 plus O give what? 2 O2s. Okay, and we know that process is what? Is slow. The reason it's slow is those two collide with each other, the chance is slow. So kind of like two people in a far distance. You need them to collide, they may pass, or they may go above. The chance for them to bring them together to collide to make a reaction, that chance is slow. That's why normally ozone would not be destroyed. But with the help of something, some other species, that process can be speed up. And those species are called free radicals. Okay, free radicals. Now, the free radicals can be naturally occurred. Okay, can be naturally occurred. So here this topic we call natural ozone destruction, meaning what? Natural process generates these free radicals to what? To help O3 and O2 what? To collect. Does that make sense? Okay, so let's take a look. What are free radicals? Okay, why natural process generated free radicals? Okay, first, free radicals are chemical species with one or more unpaired electrons. Or you can say one or more single electrons. If you remember the Lewis structure we drew before, those electrons are always what? In pairs. Is that right? No matter a dash means what? A pair of bonding. Or the ones like these dots. Like these dots we show here, we call this what? What do we call these? Non-bonding or what? Lone pair. Is that right? You can see all these electrons are actually coming in what? In pairs. Right? In pairs. But in free radicals, okay, in free radicals, there are electrons that are not paired. Single. Okay, single. And that's why we call them free radicals. And what's unique about these free radicals is because of the single electrons. Think about electrons always want to what? Want to be paired. Because of those single electrons, those free radicals are what? Highly reactive. Reactive means what? They want to bond with something. Because the electrons are desperate to what? To get paired. Okay, for example, here is the species generated by nature. Okay, we know lightning, okay, when there's lightning with a lot of energy, can promote the reaction of nitrogen and oxygen gas in the air, right? We know we have a lot of nitrogen and oxygen in the gas in the air. And those two normally don't react with each other. Think about we have 71% of nitrogen, 20 what? 70-80% of nitrogen, 21% of oxygen. They exist for millions of years. The Earth, the age of Earth, they don't react. But lightning provides energy for those to react, to give this molecule called what? Nitrogen monoxide. If you look at this molecule, if I ask you to calculate the total number of electrons, how many?
6 for oxygen and
Yeah, take your time. Very good. I like the way you're learning. It's great.
nitrogen.
5. So total is what? 11 means what? 1 ampere, right? It's even. It's an odd number. It's not an even number. So definitely there's gonna be 1 electron what? Single, right? Not paired. And because of that, this gas, NO, is a what? Free radical. That's one of the examples showing you naturally lightning can generate free radical. This is another process. This is what? Water. Water is a lot in the water vapor. But by radiation, sometimes we do get very high energy radiation from the universe, okay, and from the universe or from the sun. But those radiation, if one of the high energy radiation hit water molecule, can split the bond between O and H, half and half. So that means oxygen will carry what? A single electron. Hydrogen will carry electron. So that's also a common, naturally occurring free radical. OH. Okay, OH. So these are, again, the background of free radicals. Again, we said these free radicals will help what? Remove ozone. Okay, deplete ozone. But these are naturally occurring radicals, so we call what? Natural ozone destruction. And here are the reactions showing you how they did it. Okay, it actually gets involved in the reaction. You can see there are 2 steps. First step, this is NO, the free radical, right? It reacts with ozone, goes above to react with ozone to give what? O2 and what?
Nitrogen.
NO2. Okay, that's the first step. Then NO2 react with O to give back the NO and what? Oxygen. If you look at these two steps, you will realize that normally we said these two collide with each other, chance is what? Low, right? But with the help of the NO, what happened? They're actually helping them to what? To move forward, right? This guy react with what? O3 to give what? This guy. And then whatever this guy gives, the NO2 will react with what? With the O to give you what? O2. So if you add these two steps together, you will find something very useful. Interesting is, add these two reacting together means you add everything on the right, left together, everything on the right together, and then you cancel the one that are on both sides. Okay, you see that? You see the NO on this side, NO what? This side. NO2 on this side, NO2 what? On this side. So you cancel this, what do you see here? Is that a reaction, right? Is the one we see ozone gets removed. So the reaction doesn't change, but what happened is with the help of this guy, the reaction becomes what? Easier. Right? Think about just like, normally I said those two guys may pass around, they don't collide. But with something between, they can help them what? Bring them together. Okay, so the process, this guy, even though the net process shows, hey, this is the same process, but it's a lot faster than before without NO. Okay, without. That's why NO will destruct ozone. And why is that? Because NO is a free radical. And another fact is, you notice that in the first step, NO gets involved to react with what? O3. But in the end, take a look. What happened? You get NO back. Is that right? So that means what? The NO is what? Not consumed. You first get involved. In the end, what? Spit it out. Right? You regenerate this NO. Means what? One single NO can go what? Can start this process what? Again. So this NO can be used many, many times to do what? To destruct ozone. And we call this guy a catalyst. What catalyst means? It means it will not, it participates in the reaction, but what? Not consumed. So that means this NO can what? Can do this process again. And then again and again. So one NO can do a lot of help to what? Bring these two guys together to O2. Okay, to O2. Okay, that's natural ozone destruction. Okay, natural again means these species are not only generated by human activities, but what? By natural process. Okay, inevitably we have those processes helping ozone destruct. Okay, this practice, I want you to, after that you can try it at home, is ask you to further understand what are free radicals. Again, free radicals are species what? With single or unpaired electrons. Okay, here is the Lewis structure of OH free radical. This is the structure of NO free radical. And you can see that you follow the same step of drawing Lewis structures. But in the end, one of the atom has to what? Have 7 electrons. We know octet is what? 8. But you have a single electron, there's no way you can satisfy everybody to become 8. One guy must have what? 7. In this case, you can see this is oxygen. It has how many? 2, and what? 7, right? This is nitrogen. 4 plus 2 plus 1 is what? 7. But the rule is the same. You calculate the total, you bond them together, you satisfy one guy, and the other guy will not be satisfied. Because what? The number of electrons is what? Is odd. Right? It's not even number. Okay. In contrast, for example, C. In contrast, NO2 has no unpaired electrons. Why is that?
It's an even number.
Because you have what? 2 nitrogen, right? One nitrogen has how many? 5. So 2 nitrogen is what? 10 plus 6 is 16. So you can draw a Lewis structure of it. Okay, in this case, they tell you already. They tell you place one of the nitrogen as a central. You see that? Okay, one nitrogen is central, that means another nitrogen and the oxygen is surrounding. You can try, use our rules to draw Lewis structure. This is the Lewis structure NO2. You can see that all electrons are paired. Okay, all electrons are paired. So again, these are some practice to further practice these unique chemical species, and because of these single electrons, they're super reactive. Okay? And finally, we want to talk about, besides natural ozone destruction, we do have extra human activities to even speed up the ozone destruction process. And that's become very new, actually. In recent years, we realized we're destructing ozone. Natural process is destructing, but does not cause concerns. Not until recently, we found our human activities are adding more than natural processes. Okay, so this is the background. You can see that. The data suggested something beyond natural sources was responsible for this destructing the ozone layer. And you can see this is the picture of the ozone concentration. Okay, it's a Dobson units. I don't even know what Dobson, but we can see that higher, like a reddish color, the concentration is what? Is higher. More purple, bluish, the concentration is what? Is lower. You can see this is the satellite picture of the ozone from the South Pole. Okay, from the south end of the Earth. You can see that this is from 1979 all the way until 2008. You can see that what? The ozone concentration is getting what? Lower and lower. Okay, you see this is our Arctic pole. The purple and blue colors are where there is the least ozone. Okay, this means what? This means if the concentration of the ozone on this pole, if people, also there's no living people living there, but there's a concern living things will be what? Will be damaged if under this area, because the ozone layer is too low, and will be more UV radiations than ever anywhere else on the Earth. Okay, and also there's some readings on the website I provided in my notes to explain to you why the ozone hole, becomes thinner and thinner, starts here on the South Pole. There's a reason, because of the structure of the Earth. Okay, and this is another picture, shows you the concentration of ozone has decreased dramatically since 1989. Okay, since 1989, you can see this is the ozone concentration. Since 1989, you can see that start to decrease dramatically. Okay, and the minimum concentration was only 73 Dobson unit in 1994. Okay, and of course we need to find out why. What is happening starting from 1980s? Okay, what are we doing? What are we making? Right? We said these are not beyond the natural source. So what are we making to cause the ozone to deplete? Okay. The evils, okay, now we know, are these two guys. Started with these two guys. Okay, called a group of compounds called chlorofluorocarbons, shorted with as CFC. Okay, you see CFC, everybody know what the CFC is. Okay, the reason we call them chlorofluorocarbon is they have a structure like this. Again, these are Lewis structures. You can see that. Central is carbon. This guy has 3 chlorine bonded to it. This guy with a fluorine. This guy has 2 chlorine and 2 fluorine bonded to it. Okay, they're both CFCs, chlorine fluorocarbon. Okay, this guy is called has a brand name called Freon 11. This guy is called Freon 12. Okay, they are freons. Okay, and when we made those molecules, okay, these freons, they were invented to be used as refrigerant gases. Okay, what are refrigerant gases? In the refrigerator, to us as a coolant, and also AC units, to bring down the air, the cooling in our home, in our fridge. And they're actually revolutionized the gases. Okay, people love these gases for these reasons. Okay, I make it in bold letters. These gases are non-toxic, odorless, colorless, and what? not flammable. Think about how good it is. If you have some commercial products, they're not toxic. They don't cause any fire, and they don't smell bad. So they're what? They're perfect substitute for ammonia or sulfur dioxide people used to use for cooling, for air conditioning. So people were happy about these products. Okay, products. And also they use these to make insulation properly and also as propellant when you use the aerosol. They still use that. If you use the aerosol spray can, some of those foaming, they still use those in a small amount. Okay, so these are how or why we made those, we invented those. But, like I said, these are the evils we found out later. Besides their advantage of using the AC air, they are ozone damage. Okay, we know they're unreactive. They don't cause fire. However, when those gases are released, because no matter how good your AC unit fridge is sealing, there's gonna be leaking of these gases because they're gases. And also when you fill those in industry, they all have to release of what? These gases in the atmosphere. So when those gases in the air rise to the above, the stratosphere, and when they're exposed to UVC, this is what happened. When they're exposed to UVC, the C-chlorine bond breaks into these two species. Okay, this bond is how many electrons? 2 electrons. And 2 electrons with under UVC, these two bond breaks means carbon carries 1 electron and what? Chlorine carrying this one. Okay, this is big. Okay, it doesn't cause much problem. But chlorine atom is what? Is small. And because it has 1 single electron, we call this guy a what? A single unpaired electron, we call this guy a
Free radical.
A free radical. And a very tiny free radical. And what it does is these 4 steps. Chlorine react with what? Ozone to give you whatever this is. These 2 of those combine together and under UV they will split again. And then this guy will also split again into oxygen and chlorine. So these are 4 steps. Again, like we said earlier, if you add these 4 steps all together, everything on the left side, everything on the right, and you cancel species on both sides, this is what you got. 2 ozone becomes what? 3 oxygen. So it means what? Chlorine helped ozone to become what? To become oxygen. And what's worse, like we said earlier, we started with 2 chlorine atoms. Take a look, what happened? In the last 2 steps, these 2 chlorine atoms what? Came back. Regenerate means what? You don't need much chlorine to cause this damage. Because this chlorine can be what? Reused to do things again. And again, we call this what? Catalyst. Okay, they can be regenerated later. Okay, regenerate later. Okay, and this one, okay, like I mentioned earlier, okay, why the hole, okay, ozone hole first occurred over Antarctica. You can see the lower atom stratosphere over the South Pole is the coldest spot. This create a called a polar stratospheric clouds, which help support the chemical reactions and produce active chlorine. So basically the reaction happened the most around that area. Okay, that results in seasonal variation of ozone hole. So you can see this is the picture showing the seasonal variation of chlorine concentrations. Okay, temperature, and also during different season, you can see the ozone concentration is lowest around what the July, June, July, and also lower in Antarctica than Arctic. Okay, so after we know that, global corporations, they have to do something, otherwise the ozone will definitely be totally destructed. So they signed a protocol called the Montreal Protocol, of course, signed in Montreal in 1987. Okay, 1987. The goal of this protocol is to phase out the production of CFCs by 2010. Okay, by now it's completely phased. Okay, and even that, the recovery of ozone concentration. Okay, remember where ozone content is already depleted because it takes years for us to realize CFC is damaging ozone. So the recovery ozone concentration is very, very low, and it's anticipate that it takes until 2070 for the ozone level to return to the level of 1980. Okay, when we first started to use CFCs. Okay, recovery, it means ozone concentration is increasing, but it takes, okay, it's take like, this is the thousands of tons of CFCs produced. You can see this is the Montreal Protocol site signed, and then you can see that the production globally is decreased. Okay, is decreased. Okay, and this is the picture showing the recovery of ozone concentrations. Now, because CFCs are such great refrigerants, and if we cannot use those, we have to find what? Alternatives. Okay, alternatives. So one of the alternatives we have ever used is by introducing hydrogen in the molecule of CFCs, and we call those HCFCs. Okay, HCFCs. HCFCs have one advantage over CFCs is because of the presence of the hydrogen. They decompose faster in the troposphere. I mean, in the ground level, okay, lower level. So they're decomposed. Once they decompose, we know free radicals what? Are reactive, maybe bumping into something else. So they do not accumulate much above in the stratosphere to what? To deplete ozone. Okay, that means chlorine atoms even break apart, just stay around the ground level because they break down faster. But the problem is it still has CCl bond. Means what? There is still a potential of what? Generating chlorine atoms to affect ozone. Okay, even though it's less severe than CFCs, but it will still pose an adverse effect on the ozone layer. So the next stage of alternatives for CFCs are these gases called HFCs. Now you can see in the structures there's no what? No chlorine, called hydrogen fluorocarbon. There's no chlorine. Okay, there's no chlorine. Means if no chlorine, CF bond is very strong. It's very rare that CF bond can break. So there's no chlorine means there's no generation of radicals. These gases don't break down ozone. Has no adverse effect in ozone. Okay, they are actually used as refrigerant gases in air conditioning applications. Okay, I don't know if you have heard of it. If you working in autos, R32 and R125, these are both HFCs. Okay, these are the structure. You can see a carbon, fluorine, and hydrogen. Okay, the name again, HFC stands for hydrogen fluorocarbon. Okay, hydrogen fluorocarbon. And here is a quick practice. Okay, quick practice asking you, can you draw the structure of HFC 134? Okay, a 134 has a formula of C2H2F4. It means 2 carbons. See, this is 2 carbons, 4 chlorine, and 2 hydrogens. Okay, this is structure. Again, you can try it. Okay, after you go home and cover the keys and try to draw the structure of HFCs. And they give you a hint already. I actually put 2 fluorines on each C carbons. Okay, you have 2 carbons, 2 fluorine each carbons. Okay, again, the rule is the same. Everybody's satisfied what? The octet. Okay, they didn't show the electrons on the fluorine, but when you draw the Lewis structure, it's better to put the electrons on the floor. Okay, and finally, one of the newest classes of these alternatives is called HFOs. Stands for hydrogen fluorine olefins. Okay, the olefins is this CC double bond structure. Okay, so you call it an alkene, but we call it olefins. And it has hydrogen, has fluorine, but olefins. Okay, this is one of the examples. DuPont, okay, and Honeywell and DuPont, they co-announced the invention of this alternative that is approved, okay, for use in Europe and the US and Japan. Okay, they're introduced later on, and this is one of the newest generation of alternatives for F-gases. So that is all for chapter 2. Okay, we studied ozone, and we know later on we found out ozone can be destructed by what? By radicals. Okay, and radicals normally can be generated by natural sources, NO or OH radical. But natural sources does not cause a concern for depleting the ozone. But our human activities, especially after we invented CFCs, we found chlorine radicals are much worse and more effective than natural resources. And we found there's a problem of even creating an ozone hole in the south pole of the earth. So we started finding alternatives, and make sure you know these alternatives. What the differences are they? Okay, for example, HFCs means what? Means HCFCs means they add hydrogen. Okay, HFC means what? No more chlorine. Okay, there are generations of alternatives. The main purpose is to solve the problem of ozone depletion and hope the ozone level can recover to the year before we started using CFCs. Okay, let's stop recording. Then I'll practice a few things.